Hi everyone, welcome to the presentation of our paper titled Workload-aware materialization for efficient variable elimination on Bayesian networks. My name is Cida Maslay from Aarhus University. This is a joint work with Martino Ciaperoni from Aalto University, Aristides Gionis from KTH, and Michael Mathiostakis from University of Helsinki. Let's start with a brief background on Bayesian networks. Bayesian network modeling is an important inference tool for many real-world applications where complex probabilistic modeling and reasoning is required. Invention of Bayesian networks by Judea Pearl in 1980s revolutionized artificial intelligence by changing its focus from logic to probability. One of the real-world applications that benefit from Bayesian networks is the database management systems. Bayesian networks have been used for the tasks of selectivity estimation, approximate query processing, and predictive queries. To formally define, a Bayesian network is a probabilistic graphical model that represents a set of random variables and their conditional dependencies and independencies via a directed acyclic graph. Each node in a Bayesian network represents a random variable, each edge represents the dependency of the child on the parent variable, and each node is associated with a conditional probability table that quantifies the probability that the node takes a particular value conditioned on the values of its parents. One important property of Bayesian networks is that each variable in a Bayesian network is conditionally independent of all its non-descendants, given the values of its parents. This way, the joint probability distribution of all the variables factorizes nicely into conditional probability tables associated with the nodes of a Bayesian network. In this paper, our aim is to efficiently process inference queries over a Bayesian network. For example, given a Bayesian network learned over a database, one query could be among young females who commute by car, what fraction live in big cities, which can be cast as a conditional probability query. To answer such a query, we need to solve the inference task. However, let us first remind that inference in Bayesian networks is NP-hard, and even worse, approximate inference is also NP-hard. In our setting, given a Bayesian network, we consider queries specified by a set xq of free variables and set yq of bound variables. A query can be naively answered by eliminating the set zq of variables that do not appear in the query from the joint probability distribution. To do this, basically, we would need to first perform a join of all conditional probability tables into a big table H, which represents the joint probability distribution. And for each bound variable, we filter out the values that the query asks, and for each irrelevant variable to the query, irrelevant meaning this set zq, we compute a sum over each group of values of variables, so we do marginalization, and the resulting table is the answer to the query. Running time of this naive approach is r to the power n on a Bayesian network with n discrete variables that take r possible values each. Variable elimination algorithm improves the running time to nr squared by taking advantage of the factorization of the joint probability. Variable elimination algorithm takes as input an elimination order and processes each variable one at a time by performing natural joins only over the conditional probability tables that contain the variable. Elimination order gives rise to an elimination tree in which leaf nodes correspond to the original conditional probability tables, and each internal node corresponds to an intermediate vector that are created during the execution of the variable elimination algorithm. As an example, consider the query with the free variable t and the bound variable a. Here, sigma denotes the elimination order. The first variable that the algorithm will eliminate is variable a. Variable elimination first finds the conditional probability tables that contain A. Here they are given as the children of this node A, and performs natural join over these tables Then these two conditional probability tables are replaced with the resulting intermediate factor at node A, which we name psi of A. Repeating this operation for other variables in the order, we end up with this tree in which the parent-children relation reflects the join operation, the direction of join operation. The intermediate factors that are created during the execution of variable elimination can be costly to compute every time a query requests them. And the same intermediate tables can be used for the evaluation of many different queries. What we can do smartly would be to precompute and materialize useful tables that bring the largest computational benefits. In other words, the tables that are involved in the evaluation of many expensive queries. Then we first need to formalize what is a useful factor is. So a materialized factor is useful for a query if it is one of the factors that are computed during the evaluation of the query, and if there is no other materialized factor that could be used in its place with greater cost savings. So what this means, what the second point means is basically that, for instance, if we have materialized the factor at nodes S and E, then the materialization at node E is useful compared to the materialization at node S, since the precomputation at node E allows us to prune the subtree which already contains the subtree at node S. So in this setting, if we have materialized both the factor at S and both the factor at E, then we cannot say that S is useful for the query since E is already useful for this. To formalize how much savings we can obtain thanks to such materialization, we need to define the computational cost of the operations performed during variable elimination. We first define partial cost to denote the computational effort required to compute the corresponding factor given the factors of its children. We can also define the total cost at node U as the computational effort it takes to compute the corresponding factor at node U from the start of the variable elimination. In other words, as a sum of partial costs of the nodes in the subtree of node U. We can now formalize the benefit of materializing a set R of factors associated with the nodes of the elimination tree as the expected savings we obtain by materialization, where the expectation is over the randomness of the query workload. In this paper, we study two variants of the problem of finding the optimal materialization. One formulation assumes space budget as knapsack constraint, and the other formulation assumes cardinality constraint on the number of intermediate factors that we want to materialize. Accordingly, we provide dynamic programming algorithms that can find optimal materialization in pseudo-polynomial time for the first problem that admits knapsack constraint, and polynomial time for the second problem with cardinality constraint. We also show in the paper that the benefit function is monotone and submodular, so one can always use the greedy approximation algorithm. But we also know that dynamic programming already gives optimal solution. In our experiment, we use two real-world Bayesian networks, and all the data sets and our implementation is publicly available online. Finding the optimal elimination order is NP-hard. Therefore, we have tested all the heuristics available in the literature that have been shown to perform well. We have tested for each Bayesian network and proceeded with the elimination order that results in the smallest elimination tree. We compare our proposal variable elimination with materialization with the junction tree algorithm from 1998, which also exploits materialization by the calibration of the tree. And we also tested our algorithm with the index junction tree proposed by Kanagal and Deshpande, which builds an additional hierarchical index built on the calibrated junction tree. We have tested two different workload schemes, one uniform in which each variable has equal probability to appear in a random query, and the other one is skewed workload, in which a variable appearing in a random query correlated with its elimination order. For each workload scheme, we have generated 250 queries. As part of our experimental results, we observed that materialization improves the execution of variable elimination algorithm to a great extent, an average gain of 70% savings in the uniform workload case, with the maximum saving reaching up to 99%. And we also show in the paper that variable elimination with materialization provides more efficient querying compared to junction tree-based baselines. And not only the online inference phase is efficient, the offline materialization phase of our proposal also is quite efficient and in general uses very little space compared to the other algorithms, junction tree and the index junction tree, that also exploit materialization. So to conclude, we show that a small level of materialization for variable elimination offers significant advantage over junction tree-based algorithms. And we have more efficient inference in the online phase and faster and lighter precomputation in the offline phase. And we show that this basically implies that there are many interesting avenues for future work. For instance, what other Bayesian network inference algorithms we can hope to exploit materialization, and what other machine learning models that can benefit from materialization. Thank you for your attention.